So every physical system in the universe can be described by an element of a Hilbert space because it can be in a superposition state. But if we measure that system, then it will probabilistically jump to an eigenstate of the relevant observable. And if we don't measure it, then it will evolve according to Schrödinger's equation. Schrödinger's equation is linear, which means that the resulting evolution is linear, and can therefore be described by a linear operator U, which turns out to be a unitary operator. The measurement postulate tells us that if we measure an observable A, and we calculate the average result that we're going to get from all the measurements, then that's just equal to the expectation value. And because we know how things evolve, we can see how the expectation values evolve. And we can see from here that our normal quantum mechanics sort of groups the evolution operator with the state. So we think of that as normal. So we've written that here. That's actually got a name. That's a version of quantum mechanics, or at least a version of the calculation tools in quantum mechanics known as the Schrödinger picture. But we could just as easily have grouped it differently. We could just as easily have decided that the things that evolve are not the states, but in fact the operators. And if we did that, we'd be working in the Heisenberg picture. It's important to stress that neither is right or wrong, they're just different ways of writing the theory. So in the Heisenberg picture, the states don't change, but the operators do. In the Schrödinger picture, the operators don't change, but the states do. So we can use this diagram here as a definition of how the Heisenberg operators evolve over time. And if you start with your initial time being where the Heisenberg operators correspond with the Schrödinger operators, then you've got a relationship between the two. Okay, so before we go on, I want you to try and prove two things. The first is that if we start off with an operator where the Schrödinger operator is just the product of two operators, so C equals AB, then that implies if we go into the Heisenberg picture that the Heisenberg operator C is just equal to the Heisenberg operator of A times the Heisenberg operator of B. Have a go and see if you can prove that cold.